Hello dear students, welcome you all to this session. So here in this session we are going to discuss about the AIET 3 JEE solutions of class 11 chemistry. Okay, so I have selected some questions for you from this exam which are very important and some questions which you feel very difficult to solve. Okay, so concentrate properly from the beginning. So let's move on to the first question. So the first question for the session is question number 31 of your question paper. So the question says, consider the following statements. So two statements are given to us. We have to find out the correct option from the given four options from the two statements. Okay. Statement 1 says the second ionization potential of magnesium is greater than the second ionization potential of sodium. So listen. So we have sodium and also we have magnesium. Okay. So the electronic configuration for sodium will be 1s2, 2s2, 2p6 and 3s1. And the electronic configuration of magnesium will be 1s2, 2s2, 2p6, 3s2. Okay, the atomic number for sodium is 11 and for magnesium it is 12. So these are the electronic configuration for both the atoms. Okay. Now, what is ionization potential? The energy required to remove the electron from the outermost shell is called as ionization potential. Okay. If I'm going to remove the last electron, that is called as the first ionization potential of that atom. Got it. So suppose if I remove this 3s electron from sodium, I will call this as ionization energy 1. And if I'm going to remove the last electron which is present in this 3s orbital, in 3s orbital we have 2 electrons, right? I want to remove the last electron of this magnesium and the energy required to remove that electron is called as the ionization energy or the ionization energy 1 for that magnesium atom. Okay. After the removal of this first electron, I will get the configuration of sodium as 1s2, 2s2, 2p6, 3s0. 3s0. And for magnesium, it will be 1s2, 2s2, 2p6 and 3s1. So if you look into the first ionization energy for both, magnesium 3s orbital is fully filled. So the fully filled configurations are more stable, right? So the energy required to remove the electron from 3s orbital of magnesium will be more. Okay, so the ionization energy 1 will be more for magnesium. But after the removal of that one electron, I have to go to the next electron, which is actually called as a second ionization potential. So the removal of second electron leads to the second ionization potential of each atom. So to remove the second electron for sodium, I have to go to the inner shell, which is the second shell. And also the inner shells are fully filled. Okay. And coming to magnesium, the second electron is present in 3s orbital itself. So what do you think of this? Second shell is more closer to the nucleus. So the energy required to remove the electron from the second shell will be more. So the ionization energy 2 for sodium will be more compared to the ionization energy for magnesium. Okay. So the second ionization potential of sodium is greater than the second ionization potential of magnesium. Okay. So here it should be sodium and here it should be magnesium. So statement 1 is false. Okay, this statement is not correct. And statement 2 says, the first ionization energy always increases as we move across a period from left to right. Is it so? Will it always increase on moving across the period? No. We do have some exceptional cases, right? Like for example, if I go for nitrogen and oxygen, nitrogen atomic number is 7, oxygen's atomic number is 8. The general trend for ionization energy says that across the period from left to right, the ionization energy value should increase, right? But due to the half-filled stable electronic configuration of nitrogen, which is 1s2, 2s2, 2p3, and for oxygen it is 1s2, 2s2 and 2p4. 2p4 is partially filled and 2p3 is half filled for nitrogen, right? So we have 3 p orbitals and 3 electrons are there, so it is an half filled configuration. So half filled configurations are more stable, right? Half filled configurations are more stable. So the energy required to remove the electron from the more stable configuration is more. So the ionization energy is decreasing for across the period for nitrogen and oxygen. Okay. It doesn't increase always, but the general trend is it increases. But there are some exceptional cases in between the periods in the periodic table. Okay. So statement 2 is also false. So both 1 and 2 are false. So option B is the correct answer for this question. Okay. Now moving on to the next question. In copper plus, the number of shells occupied, subshells occupied, used orbitals and unpaired electrons respectively are. So we are supposed to find out the 4 terms. Okay. First of all, let me go for the atomic number of copper. It is given in the question, it is 29. So copper plus means copper has lost 1 electron. So totally there should be only 28 electrons. Okay, let me write the configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s, 0 and 3d10. 4s0 and 3d10. So this is the configuration for copper plus. For copper it is 4s1 and 3d10, and for copper plus it is 4s0 and 3d10. Okay, so one electron which is present in 4s orbital will come out, giving rise to this configuration. Now we have to find out the number of shells occupied. Number of shells occupied. So here if you see the number of shells which are occupied by the electrons for copper plus. So we have shell number 1, we have electron since shell number 2, and also we have electrons in shell number 3. So the number of shells occupied is 3. Okay. And next coming to the number of subshells occupied. Number of subshells occupied. So subshells. Subshells means that S, P, D. Okay. So I have 1s, 2s, 2p, 3s, 3p and 3d. So there are 6 subshells getting occupied for copper plus. Okay. And the third is the number of used orbitals. The number of used orbitals. So for 1s, we have only 1 orbital. For 2s again, 1 orbital. For 2p, we have 3 orbitals. And for 3s, 1. And for 3p, 3. And for 3d, it is 5. Total number of d orbitals for an atom is 5. right? Now, if you count this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the number of used orbitals is equal to 14. Okay. And the number of unpaired electrons. Number of unpaired electrons. So if I fill all these electrons in this orbital, in 1s I have 2 electron, in 2s I have 2 electron, in 2p I have 6 electrons, and 3s has 2 electrons, 3p also has 6 electrons, okay, and 3d is having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay. So all the orbitals are occupied and we don't have unpaired electrons in copper plus configuration. So the number of unpaired electron is equal to 0. Clear? So the answer is 3, 6, 14 and 0, in which option C is the correct answer. Okay? Option C is the correct answer for this question. Clear? So now moving on to the next question. Question number 34. Calculate the threshold frequency from the below mentioned data of wavelength of radiation, irradiated and velocity of electron ejected out. So the first column is about the wavelength and the second is about the velocity. We have to find out the threshold frequency. So threshold frequency is the minimum amount of frequency required to eject an electron, right? So it is denoted by the letter nu naught. So nu naught we have to find out. So how to find out? We have to find the answer from the kinetic energy formula we know. So we know that kinetic energy is equal to h into nu minus nu naught, which is actually equal to half mv square. Half mv square is the kinetic energy, right? Now we have the values of wavelength and velocity. You can substitute. On substituting the values for first experiment. So this is experiment number 1 and this is experiment number 2. So for experiment number 1, the lambda value is given as 500 nanometer. Lambda value is given as 500 nanometer. If I convert this into meter, it will be 10 to the power minus 9 meter. So the new value, nu is equal to C by lambda. We all know that. So the C value is, C is nothing but the speed of light. It is 3 into 10 to the power 8 meter per second. And the lambda value is 500 into 10 to the power minus 9, which is actually equal to 6 into 10 to the power 14 per second. Okay. So this is the frequency for first experiment. Now, if I substitute this frequency value in the kinetic energy formula, I will get h into 6 into 10 to the power 14 minus nu naught, which is equal to half m into v. So v is given as 100 into 10 to the power 5, right? Velocity is 100 into 10 to the power 5 the whole square. This is for the first experiment. Then coming to the second experiment. So for experiment number 2, lambda value is given as 450 nanometer, which is equal to 450 into 10 to the power minus 9 meter. Now the new value will be C by lambda. So C is 3 into 10 to the power 8 meter per second divided by 450 into 10 to the power minus 9. This will give 6.67 into 10 to the power 14 per second. Okay. Now if we substitute this new value in the kinetic energy formula, we will get h into 6.67 into 10 to the power 14 minus nu naught, which is equal to half m into v. So the velocity is 200 into 10 to the power 5, the whole square. Okay. Now this is taken as equation 1 and this is taken as equation 2. Now what we have to do, we have to divide equation 2 and 1. So this will give us h into 6.67 into 10 to the power 14 minus nu naught divided by h into 6 into 10 to the power 14 minus nu naught, which is equal to this half m and half m will get cancelled with each other. So it will be 200 into 10 to the power 5, the whole square, divided by 100 into 10 to the power 5, the whole square. Okay. So here h will get cancelled with each other. And here we are left with, here we have 200 square divided by 100 square. So let me erase this. Let me erase this part. So I have divided equation 1 and 2. Now 200 square divided by 100 square is nothing but 4, right? 400 by 100 is 4. So I will have 6.67 into 10 to the power 14 minus nu naught, the whole divided by 6 into 10 to the power 14 minus nu naught, which will be equal to 4. Now, if I bring this entire term to the other side, I will have 6.67 into 10 to the power 14 minus nu naught, which is equal to 6 into 4 is 24. 24 into 10 to the power 14 minus 4 into nu naught. So if I bring this nu naught one side, I will have 4 nu naught minus 1 nu naught, which is 3 nu naught. And it will be equal to 24 into 10 to the power 14 minus 6.67 into 10 to the power 14. Now if I subtract these two, I will get 3 nu naught is equal to 17.33 into 10 to the power 14, and nu naught will be equal to 17.33 into 10 to the power 14 divided by 3, which is equal to 5.77 into 10 to the power 14 per second. Okay. So the threshold frequency nu naught is coming out to be option B. So option B is the correct answer for this question. Okay. So coming to the next question. In the following Lewis structure of HNO3, the formal charge, this is not change, it is charge, okay? Formal charge on the oxygen atom numbered 3 is. So this is HNO3 structure and this is our oxygen 3. So we have a formula to find out the formal charge, right? Formal charge is equal to total number of valence electrons minus non-bonded electrons minus bonded electron divided by 2. So we are going to find out the formal charge of oxygen number 3. Okay. So the total number of valence electrons for oxygen is 6 minus for non-bonded. So non-bonded electrons means lone pair of electrons. Here you can see that the oxygen has 3 lone pairs. So each lone pair has 2 electrons. So there are 3 lone pairs. So 3 into 2 will be 6 electrons. Non-bonded electrons. Lone pair of electrons. Okay. Minus bonded electron. So around this oxygen, we have only one bond, right? So one bond has 2 electrons. So it will be 2 divided by 2. So it will get cancelled with each other. 6 minus 1 is equal to -1. So the formal charge of the oxygen atom numbered 3 is -1, which option B is the correct answer for this question. Okay. Now next, coming to question number 38. Which one of the following conversions involve change in both hybridization and shape? So here, if you look into each option, let me start with option A. So the structure of NH3, the shape of NH3 is pyramidal. NH3 is pyramidal, and NH4 plus is tetrahedral. Okay, so this is tetrahedral. So the conversion involved the change in hybridization. It is not, it is involved in the change in shape, but it does not involve the change in hybridization, because the nitrogen hybridization in NH3 is also sp3, and in case of NH4 plus is also sp3. Okay, here only change in shape, no change in hybridization. Then if I come to option B. So option B has CH4. Hybridization of the carbon here is sp3, and the hybridization of each carbon atom in case of C2H6, it is also sp3. Both the carbons are having sp3. Okay, and the shape is tetrahedral for both. So there is no change in hybridization as well as the change in shape. Okay, so option B is also not the correct answer. Next, coming to option C. So here I have H2O, in which I have 2 bond pairs and 2 lone pairs. The hybridization of this oxygen is sp3, and the shape is tetrahedral. And coming to H3O plus, here I have one lone pair. So here if you see to the hybridization of this oxygen, it will be, actually there are 6 valence electrons for oxygen and 1 has been lost. So remaining 5 are there. So there are 3 bond pairs and 1 lone pair. So again the hybridization will be kind of sp3, but with the trigonal planar kind of structure. Okay. So there is change in shape, but there is no change in the hybridization. So next I'll come to option D. I have BF3, where the hybridization of boron is sp2 and the structure is trigonal planar. And next coming to BF4 minus, the hybridization of boron will be sp3 and the structure is tetrahedral. So there is a change in the hybridization as well as the change in the shape. Okay. So how to find out the hybridization? So we have one formula, right? Steric number formula, which is equal to the number of sigma bonds plus number of lone pairs. So using this formula, if you calculate the steric number, you will get the hybridization for all the species. Got it? So only in option D, we have the change in both hybridization and shape. Okay. So option D is the correct answer. Next, coming to question number 41. The quantum numbers n and l of 4 electrons are given below. Choose the one that has the second lowest energy. So now, according to Aufbau's principle, the Aufbau's order, the Aufbau's order is, the Aufbau's order is So the Aufbau order is as follows. So 1s, which is lower in energy compared to 2s, then 2p, 3s, 3p, 4s, 3d, 4p. So this is the order, right? So now let's come to the options. So in first option, we have n is equal to 4. So it is 4, shell number is 4 and L is equal to 1. So L is equal to 0 for s orbital, L is equal to 1 for p orbital, it is equal to 2 for d orbital and 3 for f orbital. And here we have L is equal to 1. So it is p orbital, 4p. And here it is 4s. So here it is 3d and here it is 3p. Okay. These are the orbitals. So we have 4p, 4s, 3d and 3p. So this is the orbital with the highest energy. Okay, with the 4p is the highest among these four. And this is the first lowest energy containing orbital. And this is the second lowest energy orbital. Okay, so the second lowest energy orbital is 4s. So it is given in option B. So option B is the correct answer. Okay. Next, moving on to question number 43. The amount of oxygen in 3.6 moles of water is. So actually 1 mole of water contains, so 1 mole of water has how many grams of oxygen? In 1 mole of oxygen, we have 16 gram, right? We have 16 gram of oxygen. So in 3.6 moles of water, 3.6 moles of water has 3.6 into 16 gram of oxygen, which is actually equal to 57.6 grams of oxygen. Okay. So option B is the correct answer. Just you need to multiply the 3.6 with the atomic mass of oxygen, which is actually the mass of 1 mole of oxygen. Okay. Next, coming to question number 47. Which one of the following elements has zero electron affinity? So what is meant by electron affinity? The energy released from an atom, okay, from an isolated gaseous atom, when an electron is added to it, is called as electron affinity. Okay. When I am trying to add an electron to an atom, so while adding this electron, some amount of energy will be released from the atom and we call that energy as electron affinity. Okay. So now moving forward with this concept, we have 4 elements: fluorine, nitrogen, krypton and ruthenium. Out of these 4, krypton is a noble gas. So noble gas have completely filled configuration, right? Noble gases have completely filled configuration. So, which is a stable electronic configuration. Okay. So, it has complete, which is highly stable in nature, which is stable in nature. Add or remove an electron to the noble gases. Okay. We cannot able to add. Correct answer for this question. Okay. Now moving on to the next question, number 49. In a particular gaseous mixture is 1:4 of number of their molecules is. So here we have the ratio of masses of two gases, and we are asked to find out the ratio of number of their molecules. Mass of oxygen. Let the mass of oxygen be W, and the mass of, and hence the mass of nitrogen will be, and the mass of nitrogen will be, W. Okay. And we know that, and we know that we know that N is equal to, number of moles is equal to mass divided by molar mass. Okay. So using this formula, the number of moles of oxygen is equal to mass of oxygen is taken as W, and the molar mass of oxygen is 32. Coming to number of moles of nitrogen, the mass of nitrogen is 4W and the molar mass of nitrogen is 28. Now taking the ratio N of O2 divided by N of N2, it will be equal to W divided by 32 in W here 28. So W gets cancelled, and here we have now moving on to the next question. The question number 52. The number of radial nodes in the 3p orbital is. So the total number of radial nodes can be calculated using one formula, and the formula is number of radial nodes is equal to n minus L minus 1, where n is the principal quantum number or it is a shell number. So for 3p orbital, n is equal to 3 and L is equal to 1. Since it is a p orbital, p subshell, it is the L value for p subshell is 1. Okay. So if I substitute here, I will have 3 minus 1 minus 1. And here it will be 1. So the number of radial nodes in the 3p orbital is equal to 1. Okay. So moving on to the next question. Question number 55. Let bond order of O2 in O2 ASF4 is X and bond order of NO in NOBF4 is Y. Then report the value of 10X plus Y. So let me take both the molecules. So ASF4 is having -1 charge. So here it should be +1. In the same way, NOBF4 compound has -1 charge on the entity and here it is +1. Okay, so we need to find out the bond order of O2 plus. So how to find out the bond order? Using the total number of electrons. So in one oxygen, I have 8 electrons and I have 2 oxygen, so it will be 16. And oxygen has lost 1 electron, so 16 minus 1 is 50. If the bond order is equal to, if the number of electrons is equal to 15, then the bond order is 2.5, right? This is the value of X. Now next coming to the bond order of NO plus. Bond order of NO plus. So now calculate the number of electrons. For nitrogen it is 7, for oxygen it is 8 and it also has lost 1 electron, so -1. So 7 plus 8 is 15, 15 minus 1 is 14. If the number of electron is 14, then the bond order will be 3. So this is the value of Y. Now therefore 10x plus Y is equal to 10 into 2.5 plus 3. 10 into 2.5 is 25 plus 3, which is equal to 28. So 28 is the value of 10x plus Y. Okay. Next, coming to question number 58. The minimum number of moles of oxygen required for complete combustion of 1 mole of propane is X and 2 moles of butane is Y. Then X plus Y is. So for complete combustion, the general formula that we need to follow for any type of alkane is for CN H2N plus 1 for any type of alkane, CnH2n, or I'll write this as for CX and HY will be, this is the alkane, and if alkane is treated with 3x plus 1 by 2 moles of oxygen, it will give X moles of carbon dioxide plus Y by 2 moles of H2O. This is the formula. And we have 1 mole of propane. The formula for propane is C3H8. And if it is treated with 5 moles of oxygen, since the X value is 3, 3 into 3 will be 9, 9 plus 1 is 10, 10 by 2 is 5. So this 1 mole of propane on reaction with the 5 moles of oxygen, it will give 3 moles of carbon dioxide plus 4 moles of water. So 1 mole of propane is reacting with 5 moles of oxygen, and this 5 is the value of X. Okay, number of moles required for propane is 5. Then coming to butane, C4H10 is butane. So for 1 mole of butane, so 4 into 3 is 12, 12 plus 1 is 13. So we need 13 by 2 moles of oxygen to give 4 moles of carbon dioxide and 5 moles of water. Okay, so 1 mole of butane needs 13 by 2 is nothing but 6.5. 6.5 moles of oxygen. Now for 2 moles of butane, we need 6.5 into 2 moles of oxygen, right? Which is actually equal to 13. So this 13 is the number of moles of oxygen required for 2 moles of butane, which is the value of Y. So therefore, X plus Y is equal to 5 plus 13, which is equal to 18. Okay, X plus Y is equal to 18. Clear? So this is how we need to solve this. Now next, coming to question number 60. If uncertainty in velocity and position of a minute particle in space are 2.4 into 10 to the power minus 26 and 10 to the power minus 7 respectively, the mass of the particle in gram is. So uncertainty in velocity, which is nothing but delta V, is given as 2.4 into 10 to the power minus 26 meter per second. And the uncertainty in position, which is denoted by X, del X is equal to 10 to the power minus 7 meter. Okay. We need to find out the mass of the particle. So here we have to use the Heisenberg's uncertainty principle, which is actually delta X into delta P greater than or equal to h by 4 pi. So since momentum is mass into velocity, instead of this P momentum, I can substitute mass into velocity. So since mass is a constant, let me keep this out, and del V is equal to h by 4 pi. Okay, h by 4 pi. So here del x is nothing but 10 to the power minus 7 into m into the change in velocity is 2.4 into 10 to the power minus 26, which is equal to the Planck's constant h 6.626 into 10 to the power minus 34 divided by 4 into 3.14. 3.14 is the value of pi. Okay. Now keep m one side and bring all other terms to the other side. You'll have 6.626 into 10 to the power minus 34 divided by 4 into 3.14 into 10 to the power minus 7 into 2.4 into 10 to the power minus 26. Okay. So here on solving this, we will have 6.626 into 10 to the power minus 1 divided by 30.144 kilogram. Now, if we solve this, we will get 0.2198 into 10 to the power minus 1 kilogram, which is equal to 0.02198 kilogram. And in terms of gram, it is 21.9 gram. It is approximated to 22 gram. So the mass of the particle in grams is 22 gram. Okay. This is the answer for this question. And this is the last question for this session. Thank you all for listening the lecture. I hope this session is very useful for all of you. So I'll meet you all with the next set of questions in the next session. Till then, take care. Bye-bye.